Good day, everyone. Welcome to this lecture on radiation. Radiation is the third mechanism of heat transfer that we learn after conduction and convection. And what is special with radiation is it doesn't require a medium, because in radiation, heat is transferred in the form of electromagnetic waves. So that's why it doesn't require any medium. Another interesting point with radiation is that radiation can occur between two bodies even when the two bodies are separated by a medium colder than both. So as you can see from this picture, the boy is separated from the fire by the surrounding air, which is at 5 degrees Celsius, and this surrounding air is at a temperature lower than the boy and the fire, and this is something not possible for conduction and convection. And one very important example of the significance of radiation is our planet Earth. So we receive heat from the sun through radiation. So without radiation, because there is no space, there is no medium in between the sun and the earth, so it's vacuum. So if the heat cannot be transferred to radiation, then the planet Earth, the whole planet Earth, will become icy cold because we don't have any external heat. But because of this radiation, we receive the heat from the sun. Right now, let's see two important points regarding thermal radiation. Number one, any surface at any temperature, as long as the temperature is higher than 0 Kelvin, emits thermal radiation in a continuous spectrum. That is from the lambda is wavelength, the lambda of 0 to the lambda of infinity. So, and let's see the example in this graph. When the object, certain object is heated, the temperature of the surface is at 4500 Kelvin, and you can see this is the distribution of the radiation emitted by the surface of the object. So it ranges from 0 to infinity, and when the temperature change, when it increase, so you can see this is the distribution. So 6000, 7500. You might notice one thing here, that is when the surface temperature increase, so you have more radiation at the lower range of wavelength. This is what you can see here. And actually, scientists has identified that the radiation involved for thermal radiation is in the range of 0.1 micron to 10 micron. That is this range. The range that I have framed it is within this range. So most of the radiation that involved in thermal radiation is within this range. Scientists give different category to the radiation with different wavelength. So here, at lower wavelength, you have cosmic ray, you have gamma ray, you have X-ray. And here at the right side, you have when the wavelength is higher, you have microwave, you have radio wave. Okay, but the wave that involved in thermal radiation for heat transfer is within this range. And second point that I would like to tell you is the amount of emitted radiation increases with increasing temperature of the body, as you can see from the graph. So when you know mathematics, so if you sum up the total surface area under the curve, so that will give you the total amount of emitted radiation. So it's very clear that when the temperature increase, so you can see the surface area under the curve also increase. So this is in line with this point, that is the amount of emitted radiation increases with increasing temperature of the body. And generally the relationship is the energy emitted or the emitted radiation is directly proportional to surface temperature power of 4. Go back to the first point, that any surface at any temperature, as long as the temperature is higher than 0 Kelvin, emits thermal radiation. Then we can come back to this conclusion that actually everything in our daily life, including ourselves, emits thermal radiation to the surrounding. So take a look to your surrounding. So you yourself, the things that you are holding to, the four walls, everything in the room that you are sitting now emits thermal radiation. This is the full range of electromagnetic radiation spectrum. We as chemical engineers are especially interested in this range, that is from 0.1 micron to 10 micron, because the waves in this range involve in thermal radiation heat transfer. People like nuclear scientists, their interest is in this range. People involved in telecommunication, their interest is within this range. So different type of electromagnetic wave have different applications, and that's why it's important to different types of people. Now let's proceed to some terminologies which we are going to encounter in learning about thermal radiation heat transfer. Let's first start with these three terms: absorptivity, reflectivity, and transmissivity. So let's see what will happen to a radiation when it falls on a surface. So when a radiation falls on a surface of an object, there are three possibilities. The first possibility is some part of the radiation could be reflected back to the environment, to the surrounding. And the second possibility is part of it could be absorbed by the object itself. And the third possibility is part of it can be transmitted, go through that object. So the definition of absorptivity, or alpha, is the ratio of incident radiation which is absorbed by a surface. And reflectivity, or rho, is the ratio of incident radiation which reflected back into space. And transmissivity, tau, is the ratio of the incident radiation which transmitted through the body. So that's why for opaque body, So it's very clear, the tau equals to 0. And we have an equation here, alpha plus rho plus tau equals to 1. And for opaque body, we have alpha plus rho equals 1. Okay, now let's proceed to a very important concept in radiation heat transfer, that is black body. So what is the black body? According to definition, so a black body absorbs all radiation at all wavelength and from all direction, falling on it and reflects none. And because of this, at a given temperature and lambda wavelength, so a black body emits the maximum amount of radiation energy. So that's why actually in actual world, a black body doesn't exist. So it is created by scientists for the calculation, for the research in radiation heat transfer. And black body is used as a benchmark, okay, as a comparison, as a standard. And so because of that, a black body is an ideal emitter. And in actual situation, what people use, what scientists use to represent a black body in the research works. So normally they use an object, a polished object, for example an aluminium polish, then they coat one layer of this material called lamp black on that surface. So according to them, this coated lamp black coated aluminium or material have very high emissivity, so which can be assumed as a black body. Okay, next let's see what is emissivity. So emissivity, or epsilon, is the ratio of the total emissive power of a surface to the total emissive power of a black body at the same temperature. So if according to this definition, so it's very clear that emissivity of a black body equals to 1. And you can see from this figure, so it gives typical range of emissivity value for various materials. And next, what is emissive power, or E, as mentioned in the definition of emissivity? So emissive power is the rate of thermal energy emitted via radiation from a surface to all directions at all wavelengths per unit surface area. And this gives a unit of watt per meter square. So it is similar to the heat flux that we have learned in conduction and convection. So right now you might have a question: how can we calculate emissive power? So the answer is Planck's law. So Planck's law can be used to calculate the emissive power of a surface at certain temperature. So this is the Planck's law. So Planck's law explains how emissive power of a black surface or black body changes with its surface temperature T and also the wavelength lambda. And if you plot this E over lambda, then you will get this graph. You get this curve. And after that, if you integrate the Planck's law, so you will get the total emissive power over certain wavelength of a surface at certain temperature. So let's say this range. So I integrate from the lambda of, let's say 400 to 760 nanometer. So I will get what is the total emissive power within this range. And if I integrate the Planck's law from 0 to infinity, so I will get the total emissive power over all wavelength. Okay, this is actually what we call what is known as Stefan-Boltzmann law. According to Stefan-Boltzmann law, a total emissive power of a black body at certain temperature equals to sigma T power of 4. The unit is watt per meter square. So as you can see, it's actually Q over A. And for a non-black body, or sometimes we call it a real body, so the total emissive power, so besides sigma T power of 4, we need to add one more term, that is the emissivity, because we know the emissivity for a black body is actually equals to 1. So for a non-black body, the emissivity is less than 1. So that's why we need to times the sigma T power of 4 with the value of emissivity. And what is sigma? Sigma is known as Stefan-Boltzmann constant with this value. Okay, now let's proceed to the two types of surfaces which we normally encounter in radiation heat transfer. The first type of surface is black surface. So we have explained previously, black body has perfect absorptivity of 1. So because of that, it is also an ideal emitter with this value of epsilon, emissivity of 1. And normally other bodies we encounter in the calculation, we normally assume, if it is not a black body, we normally assume it is a gray body. So a gray body is defined as a body with the same value of epsilon, emissivity at all wavelengths. And according to definition, so since it is not a perfect absorber and emitter, so its alpha and epsilon value are both lesser than 1. Okay, next, Kirchhoff's law. Kirchhoff's law states that emissivity of a surface at temperature T is equal to its absorptivity for radiation coming from a black body at the same temperature. So for the case of, let's say, a small object inside an enclosed room, a big room, then we can say that according to Kirchhoff's law, at thermal equilibrium, that is when the surface temperature of that small object is same as the surrounding, or I would say same as the temperature of the wall of that room, then and under this situation, the emissivity and absorptivity of that surface, of the surface of that small object, are the same, or this one, emissivity at the temperature same as the absorptivity at the same temperature. And this is actually a very useful relationship which enable us to do estimation of all the three properties of an opaque body. So this relationship, alpha plus rho plus tau equals to 1. So absorptivity, reflectivity, and transmissivity. And we know that for an opaque body, tau equals to 0. And we know there are many information or data of emissivities are available. So if we use this relationship from the data, we'll be able to get the value of absorptivity. So once we get the absorptivity with this relationship, because tau is equal to 0 for an opaque body, so it helps us to determine the value of rho. That is the reflectivity of that body. When we apply this, we need to be careful because we need to know first, this relationship is actually derived based on a basic requirement. The basic requirement is the surface temperature of that object is the same as the surface temperature of where the radiation comes from. So meaning in the example I gave just now, so the assumption is the surface temperature of that small object inside that room is the same as the wall temperature of that room. So that is the basic requirement. So in some cases, we still can use this law for the sake of the estimation of the raw value. Okay, but we need to take note if the temperature difference between the two surface temperature is very big, so I'm talking about more than a few hundred degrees Celsius, then the estimation could be wrong. So this is what we need to take note when we use this relationship, when we use Kirchhoff's law. Okay, next let's talk about a little bit on heat transfer rate through radiation heat transfer. So we have mentioned before this emissive power. So according to Stephen-Boltzmann law, so can be calculated with this relationship. So emissive power of a black surface is equals to sigma T power of 4, and this emissive power is actually heat flux, is Q over A. So from this Stephen-Boltzmann law, okay, we can come up with this formula that is Q heat transfer rate of a gray body, okay, because in actual world, so I would say all things in the actual world, they are not black surface, they are not black body, so but they are considered in our calculation as gray bodies. So to calculate the heat transfer rate, so we can use this formula, that is Q equals to A emissivity sigma temperature power of 4. So emissivity for gray body is not equals to 1. So normally it will be given in the calculation. So, and we know that if this equation we apply it for black body or black surface, so we will get A sigma T power of 4 because emissivity for black surface equals to 1. Okay, in terms of calculation, for our course, basically we will look into 3 different scenarios, with scenario number 3 to be the most important one. Of course, we will still go through very quickly on scenario number 1 and number 2. Scenario number 1 is radiation to a small object from surrounding, and scenario number 2 is combined radiation and convection, whereby we need to determine Hc, that is the convective heat transfer coefficient, and Hr is the radiative heat transfer coefficient. Okay, scenario number 1, radiation to a small object from surrounding. Example, situation that fits this scenario number 1 is a loaf of bread in an oven, or a package of meat in a freezing enclosure, or a solid iron cooling in a very large room. Okay, you can see here, object 1 is a gray body with a surface area of A1 and surface temperature of T1. So it is in an enclosure of surrounding with temperature of T2. Okay, in this situation, we know that object 1 emits thermal radiation to the surrounding, and the heat emitted from object 1's surface equals to A1 epsilon 1 sigma T1 power of 4. And at the same time, we know that the surrounding at T2 also emits thermal radiation to object 1, and the heat emitted by the surrounding, or the heat incident, okay, to object 1 equals to A1 alpha 12 sigma T2 power of 4. So if you still remember, according to Kirchhoff's law, so if the two T1 and T2, the difference is not that big until few hundred degrees Celsius. So by using Kirchhoff's law, we can assume that the value of alpha is equals to the value of epsilon for object 1 at temperature T2. And from the energy balance equation, we know that net radiation from object 1 equals to heat emitted to the surrounding minus heat absorbed from the surrounding. So that's why we have Q equals to this. And like what I've mentioned just now, according to Kirchhoff's law, so the whole equation can actually be simplified to Q equals to A1 emissivity and sigma T1 power of 4 minus T2 power of 4, with the emissivity or epsilon equals to emissivity of object 1 at temperature 2. And there is actually an example in your textbook in chapter 4.10-1, page 303. So you can have a look on that. And from this equation we obtained from the previous slide, when we equate this equation with the general equation for convection heat transfer, then we'll be able to come out with an equation which enable us to estimate the value of radiative heat transfer coefficient. So HR, so from here when we equate these two, we'll be able to get HR. When we move T1 minus T2 to the right, and A1, so we cancel one another, so we will get HR equals to this. So HR stands for heat transfer coefficient for radiation. But we need to take note on the assumptions. There are 3 assumptions in this scenario 1. That is, first, the object 1 is very small comparing to the enclosure 2. And assumption number 2 is the emissivity is the emissivity of object 1 at surrounding temperature of T2. And assumption number 3 is the whole situation, the whole condition is a vacuum, or we can say it's negligible. We neglect the convection effects. Okay, now let's move to scenario number 2, that is combined radiation and convection. Actually, in the actual situation, so both radiation and convection play significant roles in heat transfer. So that's why it's not that common unless it's in the vacuum room, a vacuum situation. So otherwise, we need to take convection heat transfer into consideration when we determine the total Q. So we have known from scenario number 1. So in this case, Q equals to A1 HR Ty minus T2, and HR equals to this. So if you want to calculate, estimate what is the Q, that is the heat transfer rate, and if you want to take, for example, natural convection into consideration, then we need to determine HC. We need to plus HC into this relationship. Then HC, so we have learned in the previous chapter in convection. So if natural convection need to be taken into consideration, we need to determine the HC, H for natural convection, whereby you need to determine all those Grashof number, Prandtl number, and you calculate the HC from there. Then you substitute the value of HC and plus this HR, then you can determine the total heat transfer rate. And in this slide, equations for determining HR are given. So this is for SI unit. The temperature should be in the unit of Kelvin, whereby this is for English unit, and a convenient chart for English unit is also provided here. But one thing to take note is when the emissivity of the object is not equals to 1, so meaning it's not a black body, so the value obtained from the figure should be multiplied by the value of emissivity to give the value of HR from here. In this first part of lecture on radiation, we have gone through some basic introduction on radiation heat transfer. We have also gone through the few terminologies, important terminologies that will be used in the radiation heat transfer and the relationship between them. And at the end, towards the end, we have gone through two scenarios. That is scenario number 1, radiation to a small object from surrounding, and also combined radiation and convection. So that's the end of the part 1 of this lecture. So we're going to meet again in part 2. Thank you for your attention.